This is my oscillations lab. For this lab, I was provided with a video of a mass that swings in an arc while oscillating on a spring. I copied the data of the x and y position using Tracker and saved it as a CSV file with the time to analyze. GlowScript should be used to create a computational model comparing to the observed data. GlowScript was also used to graph the kinetic, gravitational potential, spring potential, and net total energy. Some fundamental principles and formulas used in this lab include the period of oscillation formula, which is T equals 2 pi times the square root of m over k, Hooke's law, which is F equals Ks, and the energy formula, which is in the specific lab is delta E is equal to the kinetic energy plus, which is delta K, plus delta U of G, which is gravitational potential, plus delta U of S, which is spring potential, which equals 0 due to the energy principle. Other formulas include the kinematic formulas for final position and velocity using net force over mass as the acceleration, and the energy formulas, which include kinetic energy 1/2 mv squared for kinetic energy, mgy for gravitational potential, and 1/2 ks squared for spring potential. So for the introduction, for the results and summary of this lab, the force stays fairly constant for each time interval. The gravitational force and spring force are the only forces on the system. The observed position varies a good bit from the predicted data. The energy changes were not exactly lined up, and due to that there was variation in predicted and computed data. To start this lab, I found some initial values. The first was L naught. To find this, L was set I set f of g equal to f of s, which sets mg equal to k of s, and s is L magnitude minus L naught. Then using these equations and manipulating the equations, I found the relaxed length to be 0.1232 meters. For my computational model, I started by setting the initial conditions and constants. I set the mass to what was given, the position to my position at time 0 on Tracker, and my velocity is 0 since the mass was not moving at the beginning. G was set to 9.8, spring constant was given as 6.83, and L0 was set as to 1.123 found from earlier. L was set to the length from the spring to the ball. L hat was L divided by the magnitude, and S was set to the stretch amount, which is the stretched length minus the relaxed length. Then I set the three components of the total energy equal to the corresponding formulas I stated previously, and E equal to the three energies added together. For the while loop, I first set the time to the time of the last data point I tracked. Then defined the initial energies. The gravitational force was set to mg in the y component. The spring force was set to negative spring constant times s times that found from outside the loop initially, and the net force was the gravitational and spring force added. Then the position and velocity were updated using the net force just found. The spring was then updated in length, L hat, and S. Finally, we had to calculate the energy from the data found so far. The kinetic, gravitational potential, and spring potential were all found from the formulas found before, and the change in energy were all found by subtracting the initial energies from the energies just found. The total energy was set to three energies added together, and the total energy was found by subtracting the initial total energy from the current energy. In this lab, the total energy should stay constant due to the energy principle and conservation of energy. In this energy change graph, the total energy is always constant 0. The spring potential is in green is inversely proportional to the gravitational potential in red. In the y direction, the predicted position varies slightly and seems to have stronger and higher values than the observed data. The observed data was lower due to potential reasons such as misclicking with tracking data or external forces such as drag. In the x direction, the predicted position seems as if it is ahead and the observed data is shifted, but both are nearly similar. The observed data slightly varies from the predicted though. The first question asks if the energy principle is satisfied for my model system. The energy principle is satisfied because the energy chain graph shows total energy approximately 0, as you can see by the yellow line. The energy only transforms from one type to another, and making the energy overall conserved. The second question is to make two separate estimates of oscillation periods for the x and y positions and compare them. To find the period of oscillation of each, the x and y positions, I looked at each graph and found the number of oscillations provided by the graph, which was 5, and divided the total time at the bottom of the fifth oscillation by 5 to find each period of oscillation. The x and y periods of oscillations varied slightly in the long run, but were still different because the mass was not moving in a perfect circular motion. In this lab, the main concepts used were Newton's second principle, the energy principle, and concepts of potential energy. There was slight variation in my computational data position and my observed due to possible external forces and factors. Some reasons for overall potential errors include rounding of mass values and data points in general, error in tracking data precisely on tracker, other external forces in the system such as drag force and friction, and the forces were not completely constant in all time intervals. This is my awesome